All right, so we are recording, and let's just take a look at this slide first, and then we'll go over our warm-up. Today's Tuesday, and tomorrow we are going to have our next test. It will be on the last part of chapter 17, which is reaction mechanisms, and it will be all of chapter 13, which is on equilibrium. And we're going to go through in detail what you're going to see on your test. And then the next thing that comes up after that is on Friday, you have a lab on buffers. I didn't put it on here, but again, that reminder that you've got that extra credit lab that you want to think about doing to kind of pull up maybe a test that you struggled on a little bit. And that will be due by the 16th at the latest. Some of you already have it done, so thank you for that. So let's take a look at your warm-up for today. It is on buffers, which is what we talked about in the last class. So the solution in A is a buffer solution. It's a weak acid, okay, that's acetic acid, mixed with a salt of its conjugate base. Now the sodium acetate would break up into its ions, and the sodium is a spectator, so it's not going to be involved in anything we write down, but the acetate is the conjugate base of acetic acid, and buffers have a conjugate acid-base pair in them. So A is a buffer. We want to calculate the pH of that buffer solution, and we can do that by taking pH equals pKa plus the log of our base over our acid. Once we do that, in B, we're adding sodium hydroxide to this buffer solution. The sodium is a spectator. What's the hydroxide going to react with? Well, it's a base. So it's going to react with the acid component of the buffer. So it's going to react with the acetic acid. And then we figure out, what we run out of, what our limiting reactant is, what the excess is. And from the excess, we can calculate the pH of the new solution that we have. And then in C, we're going to add hydrochloric acid. Hydrochloric acid is a strong acid. It breaks up into its ions. The chloride are spectators. We have to decide what the hydronium is reacting with. And since that's the acid, it'll react with the base in the buffer, which is the acetate. We decide what our limiting reactant is, what our excess reactant is, and then we can calculate our pH. So let's see how we did. Oh, wow, that pops up. Oh, do I not have this plugged in? I do. Technical difficulties. Just give me a second here. Oh, you know what? That moved somehow. Now let's try that. Oh, all right. An icon moved. All right, so let's look at the first question. So this is A up here along the top, and we're calculating the pH of a buffer solution. So the acetic acid is going to react with the water. Again, acids give off their hydrogen ion or their acidic proton. So we're going to move the H plus from here to here. We end up with acetate and hydronium. And it tells us we've got 1 molar acetic acid and 1 molar acetate. Give me 1 second to. There we go. Okay. So to calculate the pH, we'll use the Henderson-Hasselbalch equation. So the negative log of Ka will give us pKa. And then we'll add to that the log of the base over the acid. Now 1 over 1 equals 1. The log of 1 equals 0. So in this case, this buffer, the pH equals the pKa. So the negative log of 1.8 times 10 to the minus 5 gives us 4.74 for our pH. Okay. Questions on how to calculate the pH of a buffer solution? So let's look at the second part. We're adding sodium hydroxide. Again, the sodium is a spectator, right? But the sodium or the hydroxide, which is a base, is going to react with the acid in the buffer. Okay, acids donate that hydrogen ion. So we're going to produce water and acetate ions. Now, strong acids and strong bases react to completion. So we have the arrow going in one direction, and we have to decide What do we run out of and what do we have in excess? So it tells us we're adding 0.10 moles of hydroxide. It gave us the molarity and the volume for the acetic acid, so we can find out the moles of the acetic acid. And it gives us the molarity and the volume of the acetate. We can figure out the moles of the acetate ion. So we have 0.10 moles of hydroxide and 1 mole of our acetic acid. The hydroxide is going to be our limiting reactant. It completely reacts. It reacts in a 1-to-1 ratio. So we're going to have 0.90 moles of acetic acid left over. Now, we're also going to be producing 0.10 moles of acetate ion. So we're going to have 1.1 moles after all of the hydroxide has been completely reacted. We've got an acid and its conjugate base in the solution. So it's still a buffer solution. We can use the Henderson-Hasselbalch equation. The only thing that's going to change is what the base to acid ratio is. Now it's 1.10 to 0.90. We added some base. It shifted that reaction in this direction. It increased the base and decreased the acid. So we get 4.83 for our new pH. Now, the pH did go up a little bit. Well, that makes sense. We added a base to it. But it only went up a very little bit because the function of a buffer solution is to resist changes in pH. It's not going to stop the change, but it's going to make the change pretty small. Now, for the last question, we're adding hydrochloric acid, and the hydrochloric acid breaks up into hydrogen ions and chloride ions. The hydrogen ions latch on to water molecules, and that's where that hydronium comes from. That's an acid. The acid's going to react with the base component of the buffer solution, which is the acetate ion. The hydrogen ion is going to go from the acid to the base. We're going to produce water and acetic acid. Now, this time we've got 0.20 moles of acid, 1 mole of our conjugate base, and 1 mole of our conjugate acid. We calculated that here and here. We don't have to calculate it again. So we still have the buffer. We've got the base here and we've got the acid here. We've just changed the ratio a little bit. So this part of the Henderson-Hasselbalch will change just a little bit and the pH will go down. Again, it makes sense that the pH went down because we added an acid, but the original buffer solution was 4.74 and now it's 4.57. Okay, it went down, but only marginally, because our buffer consumed that acid that we added to it. If we had added this amount of acid to pure water, the pH would have been significantly lower, but it's only 4.57.
Why is the 0.80 on top of the log function?
Here? Okay,
yes.
Because it's always going to be the base over the acid. The acetate is the base. The acetic acid is the acid. So it's always going to be base over acid. It's not like product over reactant. It's base over reactant or base over acid. So up here for this one, this was the acid and this was the base. So 0.1 or 1.10 over 0.90 base over acid, or 0.80 over 1.20 base over acid. Does that help?
Yes, thank you.
You're welcome. Other questions? Probably the hardest part is just figuring, what the reaction is. And what you have to remember is that if you add an acid to a buffer, it's going to react with the base in that buffer solution. And if you add a base to a buffer, it's going to react with the acid component of the buffer solution. Acids react with bases. Bases aren't going to react with bases. Acids aren't going to react with acids. Acids react with bases. Okay, what other questions do we have? Good review of buffers from yesterday. All right, so let's go back. All right, here we go. Shut up. All right, so let's take a look at your test. Okay, it is the same format as the other tests that you've taken, so you should feel, pretty comfortable with what you're going to expect. For part 1, there are 14 questions, and you have 35 minutes to answer those questions. And we've really, gone over all of this and done some review on all of these questions as well. So hopefully you'll be comfortable with the content. So potential energy diagrams, endothermic, exothermic, activation energy, what catalysts do to the activation energy, reaction mechanisms. Okay, knowing that intermediates are produced in one step of a reaction mechanism and consumed in another, or catalysts are consumed in the first step and then reproduced in another step. The rate determining step in a reaction mechanism can be used to determine the rate law. Okay, you use that elementary step, the molecularity, the stoichiometry, whatever the coefficients are, to figure out what the exponents are in the rate law. And different kinds of factors that affect the rate of a reaction. Okay, this is all from chapter 17. It's the last section of chapter 17 that we went through. And then the rest of this is all stuff from chapter 13 on equilibrium. Okay, you're not going to see any acid-base equilibrium on your test tomorrow. That will be next week. So defining equilibrium. Okay, the rate of the forward reaction equals the rate of the reverse reaction when a system is at equilibrium. Okay, what does K mean? Okay, well, K is an equilibrium constant. Okay, the bigger the value, the more product you have and the less reactant you have at equilibrium. The smaller the K value, the less product and the more reactant you have at equilibrium. Okay, this was a question that was brought up before class today. If you're given the K for a particular reaction and you reverse the reaction, the new K value would be the reciprocal of the original, because the reactants become the products and the products become the reactants. You essentially just flip it over. If you were to double the coefficients, you would square the K value. Let me get rid of, how did that come back up? Having some technical difficulties here, hold on. Huh. There we go. All right. Knowing how to relate KC to KP. KC is the equilibrium constant in terms of concentrations. KP is the equilibrium constant in terms of partial pressures. And to relate them, KP equals KC times RT to the delta N, where delta N is the number of moles of product minus the number of moles of reactant in the balanced equation. And then if we were to look at a system that's not at equilibrium and we calculate K, how will the reaction shift to get to equilibrium? So if Q is too small, then the reaction is going to shift towards making more product or towards the right to get Q to equal K. If K is too big, we have too much product. So the reaction is going to go towards the reactant side or towards the left to make Q smaller until it's equal to K. And the only factor that changes K is temperature. Okay, so those are the kinds of things we would see in part 1. Not everything, but it's a pretty good outline of it. In part 2, you have 6 questions and 45 minutes. So make sure that you can write K expressions. Remember that solids and liquids are not included in K expressions. If you're given information about a system at equilibrium, you can figure out the equilibrium concentrations and calculate K. You can calculate Q and decide whether you're at equilibrium or will the reaction shift from the right to the left or left to the right. And then the relationship between K, which is your equilibrium constant, and delta G, which is your free energy value. And there were a couple of different equations. They're all related to each other, but a couple of different equations based on whether you're looking at systems that are at equilibrium. Once you're done with part 2, which is the longer problems that you need to work out, then part 3 is where you would submit your work. Okay, same kinds of format as what we've seen on the other tests. So let's look at a couple of review questions. They're not math-based. Oh, there should be a double arrow here instead of that funky little thing there. So I'm going to give you just a couple minutes. They're more conceptual type questions. And see, for the first one, you're looking at a Le Chatelier's principle problem. So you have a reaction here. You're given that delta H is negative, so that means something. You need to identify what it is. And you're going to change these things about the system. In which way is the system going to shift to reestablish equilibrium? Okay, for the second question, again, there should be a double arrow here. You have this kind of generic reaction here. And then instead of calculating it, it tells you if Q is less than K, what will happen? 1 or 2. If Q is more than K, what will happen? 1 or 2. So I'll give you just a couple minutes to work through those. And then we're going to finish up chapter 14 and then start chapter 15 today. So let's see how you do. All right, so let's see how we did. And we'll put some answers in the chat real quick, just so that we have, a little bit of interaction there. So we have our reaction. Okay, it gives us our delta H. Since it's negative, in the chat, are we looking at endothermic or exothermic? Exothermic, good. All right. So if we were to, the pressure of the system doubles by having the volume. Remember that volume and pressure are inversely related. So if we have the volume, that doubles the pressure. If we double the pressure of the system, we throw off the equilibrium. Which way is it going to shift to reestablish equilibrium? It's going to shift to the right, it's going to shift to the left. Agreed, it's going to go to the right. This should be a lowercase 2. We've got 1 plus 3, so we've got 4 moles of gas on the reactant side, and we've got 1 plus 1, we've got 2 moles of gas on the product side. If we increase the pressure, the system is going to shift to the side that will decrease that pressure. It's going to shift to the side with less moles of gas. All right, so we've got CCl4, that should be a subscript 4, is removed as it's generated. So as we make the CCl4, it gets removed from the container. Which way is it going to shift? Towards the right. Yeah, if we remove CCl4, it's going to want to make more of what we had removed. Now, for the last one, we're going to increase the temperature. We're going to heat it up. Now, it's exothermic. That means the energy is on the product side. So if the energy is on the product side and we increase the temperature, yeah, it's going to shift away from the side that has the energy. It's going to shift towards the left. Good, excellent. All right, so let's look at the ones on the bottom. So we've got this generic equation. Again, this should just be an arrow in 2 directions. Okay, so if Q is less than K, would some reactant react to become product, or would some product react to become reactant? One or two, just put one or two in there. It's really asking us when it says some of the reactant produces product, it's really the same thing as saying it's going to the right. And if some product reacts to produce reactant, it's really saying it goes to the left. Yeah, so if Q is too small, we need to increase Q. That means product has to go up and reactant has to go down. So the system is going to be going towards the right, and it's going to do that until Q equals K. So then the reverse, if Q is bigger than K, the system's not at equilibrium, what's going to happen in that case? One or two? Two, agreed. If Q is too big, we want to decrease Q, which means that we want to decrease product and we want to increase reactant. K would then eventually, or Q would eventually equal K, and the system would reestablish equilibrium. Good. All right. So we're going to move on and finish up our chapter on acids and bases by talking about acid-base titrations, which you did do a lab on yesterday. So you should have a little bit of an idea about how titrations work. So we have a solution down here, and we have a solution up in our burette, and we're going to add the solution from the burette to the solution in the flask. And we have 2 points that are important. The first point is called the equivalence point. And when we deal with the equivalence point, it's essentially the stoichiometric equivalence point. Okay, it's where the moles of acid completely neutralize the moles of base. Now, the end point is something that we measure in lab with an indicator. And it's measured by a color change that that indicator goes through. And what we want is to have the end point, the color change, to be as close to the equivalence point, the stoichiometric equivalence point, as possible, so that this color change takes place when the moles of acid equal the moles of base. So let's look at titration curves. And a titration curve is some kind of a curve that takes a property of a solution and plots it versus the amount of added titrant, the amount of liquid that comes out of the burette and drains into the flask. And when we talk about acid-base titrations, we typically have pH as the property we're measuring. So here's an example of a strong acid, strong base titration curve. So if we look along the x-axis, we're talking about the volume of 0.100 molar sodium hydroxide that's added to our acid. So at the beginning, we don't have any base added yet, so we just have acid. And what we do is we measure how the pH changes as we add sodium hydroxide. So as we add sodium hydroxide, we can trace that change in pH. And a classic part of a titration curve is this part right in along here. Because right here is where we have our equivalence point. So this is the point where the moles of the strong acid equal the moles of the strong base. And we also have in here some indicators. And indicators change color at different pH ranges. Their endpoints are different. So methyl red, okay, changes colors around 4 or 5 for the pH. Bromethymol blue tends to change colors between like 6 and 8. And phenolphthalein is an indicator that changes colors between like 8 and 10. Now, this is a very similar titration curve. The only difference is we're looking at a weak acid being titrated with a strong base. So along the x-axis again, how much sodium hydroxide are we adding? And along the y-axis, we have our pH. So here is where we start with just weak acid in the solution. And notice that the pH of the weak acid is higher than over here, the pH of the strong acid. And that makes sense because strong acids 100% dissociate, so they have more hydrogen ions in them than weak acids do because they only partially dissociate. So as we add the strong base to this weak acid, we're going to notice that the pH goes up. It's a little bit of a different curve look here than here. But we also have this characteristic very steep change in pH here. And again, our equivalence point would be here. Okay, general look of what titration curves look like. So now we're going to do some math calculations. Okay, and they're going to be very familiar kinds of calculations. So talking about titrations is almost a good way to wrap up the chapter on acids and bases. So for this example, we have 0.100 molar sodium hydroxide, and we're going to titrate it with 50 milliliters of 0.100 molar hydrochloric acid. So this is what we're starting with in our flask, 50 milliliters of 0.100 molar hydrochloric acid. And what we want to do is we want to calculate what the pH will be before we add any sodium hydroxide. And then after we add 40 milliliters of our sodium hydroxide, and then after we add 50 milliliters of our sodium hydroxide, and then after we add 50.2 milliliters of sodium hydroxide. So we're going to look at the titration at 4 places during that titration. Let's look at A first. Actually, let's look at the reaction first. So we have HCl. Okay, there's our hydrochloric acid. We're reacting it with sodium hydroxide. Okay, there's our base. It's a double displacement reaction. We're going to produce sodium chloride and water as our product. Now, strong acids and strong bases react to completion. So there's no equilibrium here. Okay, the arrow goes in one direction, which means we're going to be looking at a limiting reactant problem. And the sodium chloride that we produce is a salt. It's also a neutral salt. So what that means is the sodium ions and the chloride ions are going to be spectators. So really, when we look at a strong acid, strong base titration, it's the hydrogen ions from the strong acid reacting with the hydroxide ions from the strong base to produce water. And we can write it this way, or we can write it this way, because we know that the hydrogen ions really don't hang out by themselves. They tend to attach to water molecules and form hydronium. They're almost interchangeable. This is kind of the shorthand way of writing it. This is really more true to what you would have in the solution. So we've got hydronium ions reacting with hydroxide ions to produce water. And again, we're going to look before the reaction starts. So that's this point here. After we add 40 milliliters of sodium hydroxide, after we add 50 milliliters of sodium hydroxide, and then after we add, and it's not really on here, but after, oh, here it is. After we add 50.2 milliliters of sodium hydroxide. So let's take a look at the math. When we look at A A is really just what's the pH of a strong acid. There's no reaction involved. This is the only thing that's in the solution. So since it's a strong acid, the concentration of the acid equals the concentration of the hydronium ion. So the hydronium ion is 0.100 molar. Well, if we know what the hydronium ion is, we can calculate the pH of the solution. So before we start our titration, the pH of the solution is 1.000. It's this point right here. Now, let's add some sodium hydroxide. So after we add 40 milliliters of sodium hydroxide, what happens to the pH? Well, the first thing we would do is we would write our reaction. Okay, again, you can just write the hydrogen ion here and just put 1 water over here, or you can write it like this. It doesn't really matter. Now, we need to calculate the moles of our acid and our base. They don't start out in the same solution, so we can't just look at their molarities. They're not relative to each other. So we would take the volume and the molarity of our acid and figure out the moles of our acid. So we have 5.00 times 10 to the minus 3 moles of hydronium ion in our solution. Again, we're just taking molarity times volume. That gives us moles. And this number is going to be the same throughout the titration because we're not changing the amount of hydrochloric acid that we have in our solution. But let's look at the hydroxide. Now, originally we didn't have any hydroxide, but now we've added 40 milliliters of 0.100 molar. Well, you have to convert milliliters to liters. And then taking the molarity times the volume gives us the moles of our hydroxide ion. So we have 4.00 times 10 to the minus 3 moles of hydroxide ion. Now, strong acids and strong bases react to completion. So when we look at the number of moles of acid we have and the number of moles of base we have, the one that's the smaller one is the limiting reactant. That means the hydroxide is going to be completely consumed. And since it's a 1-to-1 ratio, 4.00 times 10 to the minus 3 moles of this original amount is going to react, and we're going to have some left over. So once the reaction is done, there's no hydroxide left in the solution. It was reacted with the acid. Some of the acid reacted, but there's going to be some acid left over. Well, what we need to do then is calculate the pH of this new solution. We can calculate the concentration, the molarity of the hydronium ion, and then we can calculate the pH of the solution. Now, how do we calculate the molarity? Well, it's moles over liters. Here's the number of moles of hydronium that didn't react because the hydroxide ran out. But the volume is the total volume in the container. It was 50 milliliters, but we added 40 milliliters of base. So the new volume is 90 milliliters or 0.0900 liters. Okay, so we're adding the volumes together in order to calculate the molarity of our hydronium ion. Now, once we know what the molarity of the hydronium ion is in the solution, and we take the negative log of this number, that's going to give us the pH. So the negative log of 1.11 times 10 to the minus 2 gives us the pH. Now the pH went up a little bit. Now let's look at point C. We're going to add a little bit more sodium hydroxide. And we're going to do the same process. So we have our reaction. The amount of hydronium ion isn't going to change because we're not adding any more hydronium ion to our container. But the amount of hydroxide is going to change because now we've added 50 milliliters instead of just 40 milliliters. So look at what we have here. We have the same number of moles of acid and base. We're at the equivalence point, or the stoichiometric equivalence point. That means we don't have any hydronium ion and we don't have any hydroxide ion from the hydrochloric acid and the sodium hydroxide left in the container. But what we do have is water. And we know that pure water has an equal hydronium to hydroxide ion concentration. And we know that that value is 1 times 10 to the minus 7. Take the negative log of that. The pH at the equivalence point is 7. And as long as we're looking at a strong acid, strong base titration, the pH will always be 7 at the stoichiometric equivalence point. Now, let's look at D. Now we're going to add a little bit more base. We have the same reaction. The amount of acid doesn't change. So we've got 5.00 times 10 to the minus 3 moles of hydronium ion. But now look at how much hydroxide we have. Now the hydroxide becomes in excess. Not by a lot, but a little bit. All of the hydronium is going to react. We're not going to have any of it left over. It's the limiting reactant. We're going to have a little bit of hydroxide left. If we want to calculate the pH of the solution, we're going to figure out the molarity of the hydroxide ion that's left in the solution. From that, we can figure out the pOH, and then we can figure out the pH. But we have to remember, again, that the volume is the total volume in the container. And we had 50 milliliters of original acid in the flask. And we've added 50.2 milliliters of base. So the new volume is 100.2 milliliters, or 0.100 liters, which enables us to calculate the concentration. Now, the first two calculations we did, the molarity was for the hydronium ion because that was what was in excess. But this time, it's the molarity of the hydroxide ion. So if we take the negative log of that molarity, that's going to give us the pOH. If we subtract it from 14, then that'll give us the pH. So what we did is we looked at that titration curve in 4 different places, and the calculations that we've done here match up with those 4 places on the titration curve. If you're looking at a strong acid, strong base titration, this is the reaction you want to deal with. You have to figure out the moles of the acid and the moles of the base, decide what's in excess, figure out the molarity of the excess, and then from there you can calculate the pH of the solution. Questions on strong acid, strong base titrations? We're going to change it around just a little bit. All right, so let's look at the other scenario that we had on our graph. Okay, now we've got a weak acid and a strong base titration. So we've got 0.100 molar sodium hydroxide that we're adding to 50 milliliters of 0.100 molar acetic acid. Well, acetic acid is a weak acid, so what we're going to be doing is slightly different than what we did before. And we want to calculate what the pH is at various points in the titration. Okay, we're going to figure out what the molarity is before the titration starts, what it is after we add 40 milliliters, what it is after we add 50 milliliters and 50.2 milliliters. Now, before we add any titrant, this is what we have in the solution, but acetic acid is a weak acid. Since it's a weak acid, we're going to have an equilibrium that's going to be established. So we've got our acetic acid reacting with water. We're producing acetate and hydronium. We start out with 0.100 acetic acid, but it doesn't all react. Only a little bit of it does. So we're going to have conjugate base and hydronium left in the solution. We can write a K expression, products over reactants. Now, the Ka for acetic acid is a constant. You just look it up on a table. So 1.80 times 10 to the minus 5 equals x squared over 0.100. So from here, let's see if you can roll this out on your own. Do the math to solve for x. When you solve for x, x is the hydronium ion. Once you know the hydronium ion, you can calculate the pH before we start our titration. So I'll give you a minute or two. Let's see if you can go through, calculate x, and since x is hydronium ion, calculate the pH of the solution. Ooh, look at you guys, quick. The math does become very familiar. Okay, so I'm getting a hydronium ion concentration of 1.34 times 10 to the minus 3. I'm multiplying by 0.1 and taking the square root. And then from there, I just take the negative log of that, and that gives you my pH. Now remember that since I've got 3 significant digits, I want 3 decimal places in my pH. Good. All right. So we haven't started our titration yet, and here's our pH. And notice that the pH of the weak acid was higher than the pH of the strong acid because the strong acid would have more hydronium ions in it because it 100% dissociates. The weak acid has less hydronium ions in it because only a small percentage of it dissociates. All right. So let's look at the next step. We're going to look after we add 40 milliliters of sodium hydroxide. Okay, well, here's our reaction. The sodium hydroxide is going to react with the acetic acid. Okay, remember that acids give up their hydrogen ion to bases. So we're going to produce acetate ions and water. Strong bases react to completion. So we have the arrow in one direction. So we have to figure out what our limiting reactant is. Now, the acetic acid was in one solution and the sodium hydroxide was in another solution. So we can't compare them with respect to molarities because they're in different volumes. We have to figure out moles. So for the acetic acid, 50 milliliters of 0.100 molar, we have 5.00 times 10 to the minus 3 moles of acetic acid. For the hydroxide, we have 40 milliliters of 0.100. That gives us 4.00 times 10 to the minus 3. All right. So now we need to look at the moles of acid and the moles of base and decide what our limiting reactant is. It's the smaller one. So the hydroxide is the limiting reactant. It's all going to react. The same amount of acid is going to react. What's left over? All right. So all of the base reacts. We've got 1.00 times 10 to the minus 3 moles of acetic acid. All we're doing is taking the 5.00 times 10 to the minus 3 moles that we started with, and we're subtracting 4.00 times 10 to the minus 3 because that's how much of it reacts. This is how much is left over. But we're going to produce acetate as well. Now, let's think about that. We have acetic acid and acetate in the solution. That means this is actually a buffer. Since it's a buffer, we can use the Henderson-Hasselbalch equation and calculate the pH. So the Ka for acetic acid is 1.8 times 10 to the minus 5. We can find the pKa, and we're going to add to that the base over the acid. This is the base, the acetate. This is the acid, the acetic acid. So the negative log of 1.8 times 10 to the minus 5 gives us the pKa. We're going to add to that the log of 4 times 10 to the minus 3 divided by 1 times 10 to the minus 3. And our pH has gone up to 5.347. We've added some base. It's consumed some of the acid and the pH has gone up. Now, we don't have to calculate the molarities. And the reason is the base is in the same solution as the acid is. That means the volume is going to cancel out anyway. So it doesn't matter. We can just put the moles of base over the moles of acid, and it's a shorthand since we don't have to calculate the molarities. Okay, was there a question?
Yes. How can you tell that the CH3COO minus is a buffer?
Well, this by itself isn't a buffer, but because we have acid and we have its conjugate base, that's what makes it a buffer. A buffer has a conjugate acid base pair in it. And since we've got this and we've got this, it's a buffer.
Okay, thanks.
You're welcome. All right. Now, that was this point right here. This point on the graph is actually what's called the buffer region or the buffer zone. And anytime we have a weak acid being titrated with a strong base, there's always going to be a region where the pH really doesn't change much at all. And that's because during this point, there will be acid and conjugate base in the solution. There'll be a buffer, the buffer region. So we calculated the pH here. We calculated the pH here. Now let's look at C. Okay, so same reaction. We're adding our base to the acid. We're producing acetic acid, or acetate and water. Again, we want to figure out the moles. Well, the moles of the acid aren't changing. Okay, we're not adding acid when we titrate, we're adding base. Now we have 50 milliliters of base. We can calculate how many moles of base we have. Okay, the arrow is going in one direction because it's going to react to completion. And if we look, the moles of acid now equal the moles of base. We're at the stoichiometric equivalence point. That means none of the acid will be left and none of the base will be left. But we're going to be producing acetate ions. It's a 1:1:1 ratio. So we're going to have 5.00 times 10 to the minus 3 moles of acetate. Okay, well, we can't figure out the pH from this number. We can only figure out the pH if we know the hydronium ion and the hydroxide ion. So we're going to have to take this another step and think about what this acetate will do in water. Well, the acetate will react with the water. In this case, the water is going to act like the acid, so the hydrogen ion is going to go in this direction. We're going to produce acetic acid and hydroxide. Well, now we have something in solution that's going to enable us to calculate the pH because we've got the hydroxide. So we're looking at essentially a weak base equilibrium. Okay, we've got 5.00 times 10 to the minus 3 moles of acetate ion. We had 50 milliliters of acid mixed with 50 milliliters of base. So we have 100 milliliters or 0.100 liters. So the molarity of our base is 5.00 times 10 to the minus 2. Since it's a weak base, only a little bit of it reacts, X and X. Now, we can calculate X. We know hydroxide then. We can calculate the POH, and then we can calculate the pH. Now, in the previous question, we were given the Ka for acetic acid, but we're looking at a base now. Since we're looking at a base, we need Kb. And Kb is calculated by taking Kw and dividing it by Ka. So we've got our Kb that will equal the concentration of the products over the concentration of the reactants. So 5.6 times 10 to the minus 10 will equal X squared over 0.500 minus 2. See if you can calculate the pH from that. Think about when you calculate X, what X means, and figure out what the pH of the solution will be. Now remember that when you solve for X, that's hydroxide. So when you take the negative log of that, that's going to give you POH. You're going to have to subtract it from 14 to figure out pH. When you think you have it, put it into the chat. Let's see what you got.
I'm sorry, I think I missed this, but
Yep.
was 1.8 times 10 to the negative 5, the Ka value, was that a given or was
Yes. Yep. That was in the last, on the last slide. Yep. So you were given this. We're going to use that to figure out this. Yep. Agreed.
Okay, thank you.
You're welcome. All right. So 5.3 times 10 to the minus 6 is the hydroxide. So 5.276 is the POH. That means 8.724 is the pH. 3 significant digits means 3 decimal places. All right. So now, and this would be the equivalence point. Now let's go beyond the equivalence point. So our reaction is the same. The moles of acid are the same, but the moles of base have gone up because now we're past the equivalence point. That means the hydroxide is the limiting reactant, or sorry, is the excess reactant. The acid is the limiting reactant. So all of the acid is going to be reacted. Most of the base is going to be reacted, but we're going to have a little bit left over. Now, we're also going to have some acetate ion, okay, because this is going to be 5.00 times 10 to the minus 3 reacts. 5.00 times 10 to the minus 3 reacts. 5.00 times 10 to the minus 3 is produced. Now, this is a base. This is a weak base. We're going to get so much more from here, all of it, than we are from here. We're going to get just a small amount of hydroxide from our weak base that we're just going to ignore it. It's going to be insignificant. That means these are the moles of the hydroxide ion. We can calculate the molarity of the hydroxide ion. Moles divided by the total volume. So 50 milliliters plus 50.2 milliliters gives us 100.2 milliliters or 0.1002 liters. So this is the concentration of hydroxide. We can calculate the pH because we have the concentration of hydroxide. Calculate what the pH will be at this last point in our titration. Take the negative log of hydroxide, that's going to give you POH. Subtract it from 14, that'll give you the pH. All right, so POH, good, is 3.699. pH is 10.301. Good. So let's look at kind of the opposite titration. We're going to look at a weak base being titrated with a strong acid. So now the x-axis here is the volume of hydrochloric acid that's added. That means we're going to start with the weak base up here. And as we add acid, we're going to see what happens to the pH. Now, it essentially is the flip of what we had when we had a strong base weak acid. We're just starting up high and going down low. And here's our equivalence point again. This is the point where the moles of acid equal the moles of base. So a little bit of a different wording to the question this time. We're not going to have like various points along the titration. It says, what is the pH at the equivalence point when 50.0 milliliters of 0.100 molar ammonia is titrated with 0.100 molar hydrochloric acid? So the hydrochloric acid is the strong acid. The ammonia is the weak base. So we want to write our reaction first. Okay, so the NH3, there's our ammonia. Remember that because hydrochloric acid is a strong acid, it's going to break up into hydrogen ions and the chloride ions. The chloride ions are spectators. The hydrogen ions are going to link up with water molecules and make hydronium. And we know that that hydrogen ion goes from the acid to the base. So we're going to produce ammonium ions and water as our products. And because strong acid is one of the reactants, the reaction is going to go to completion. All right, we want to get to the equivalence point. Well, we know the molarity and the volume for the base. If we know those two things, we can calculate the moles of our base. Now, it doesn't tell us the volume of the acid, but it tells us we're at the equivalence point. Well, at definition, equivalence point means the moles of the base equal the moles of the acid. So that must mean we've got 5.00 times 10 to the minus 3 moles of acid to completely react with our moles of weak base. So it didn't give us this information, but we can figure that out. And they happen to be the same numbers. They don't have to be. So all of our bases reacted, all of our acid is reacted at our equivalence point, but we're going to have ammonium ions left in the solution. Now, we can't figure out the pH directly from this number because the ammonium ions, well, that's not hydronium or hydroxide. So we have to figure out what happens to the ammonium ions in water. Okay, the ammonium ions are going to act like an acid. They're going to donate their proton to the water, and we're going to produce ammonia and hydronium. Well, that's what we need to figure out the pH. Now, this is moles of ammonium. We need molarity. So we're going to take the volume or the moles of the ammonium ion and divide it by the total volume, which was 50 milliliters plus 50 milliliters. So here's the molarity of the ammonium ion. A little bit of it is going to react. We're going to get X amount of ammonia and X amount of hydronium. So I'm going to give you this. You'd look it up. The KB for ammonia is 1.8 times 10 to the minus 5. The Ka for ammonium is 5.6 times 10 to the minus 10. So now we're at the point where we're looking at just a weak acid equilibrium. So here's your Ka. Here are your products. Here's your reactants. Set up your equilibrium. Solve for X. X is the hydronium ion. You can calculate what the pH of the solution is going to be. So really the things with these problems, the beginning is different, but once we get down to the end, they become very similar types of problems. So write your K expression. You've got X squared over 5.00 times 10 to the minus 2. Solve for X. X is hydronium. Calculate the pH of the solution. All right, so I'm getting 5.3 times 10 to the minus 6 for the hydronium ion. So 5.275 for my pH. What do we think? What kinds of questions do we have on that? All right, oops. Oh, last thing we need to kind of talk about in this chapter is a little bit about indicators. So acid-base indicators are just substances that we can add to a solution, and they change colors depending on what the hydronium ion is. So as an example, we kind of looked at this before. Methylene or methyl orange changes colors around here. Litmus changes colors around here. Phenolphthalein, which you had in your lab, changes colors up around here. And no way do you need to know this. But if you look, there's a huge span of indicators that we can use, and they change colors depending on what the pH is. So if you've ever tested the pH in your pool or in a fish tank, okay, and you had those little strips, the strips are kind of soaked with, one of these indicators so that you can figure out what the pH of that particular solution is. Okay, so somebody wanted me to go back just for a second. So let's go back for a second. There was a question. How were the moles of acid and moles of base calculated? Okay, so we were given the volume of the base and we were given the molarity of the base. Okay, that was stuff we were given in the question. We can calculate the moles. It told us we're at the equivalence point. So by definition, the equivalence point is when the moles of the acid equal the moles of the base. So these numbers have to be the same. We know this number, so this number has to be the same number. All of the base and all of the acid are reacted when we're at the equivalence point, equal points. Does it help, Sarah? Okay, good. Excellent. All right. So I think I'm going to leave this slide up here. I don't think you need the indicator slide up there. And it's about 7:15. So let's take about 4 or 5 minute break. If anybody has any questions on the titrations, anything that you want to talk about during the break, that's great. And then we're going to come back and we're actually done with chapter 14 on acids and bases. And we're going to move on to chapter 15 and start talking about just a couple of other types of aqueous equilibrium. So take a break, get a drink, stretch for a couple minutes because I know 2 hours is a long time to sit here. So get up and get the blood circulating, and then we'll come back in about 5 minutes. Okay. So what we're going to do now is not information that you're going to be seeing on your tests next Wednesday. Next Wednesday will be on acids and bases. This is some of the information you're going to be seeing on your final exam on the 16th. And we're just looking at equilibria for other types of reactions other than acids and bases. And what we're going to deal with for today is what's called our solubility product. So we're going to be dealing with dissolving solids in water. So when we look at solubility, the solubility of a substance can be essentially zero if we say that a substance is insoluble or only slightly soluble, to infinite. Okay, a lot of it dissolves. And when we talk about substances that have a finite solubility, we can form what's called a saturated solution. Okay, one that has the maximum amount of solute dissolved in it. And if we put more solutes into that solution past the saturation point, we would have a heterogeneous mixture with undissolved excess solutes on the bottom. So let's use silver chloride as our first example. Now, silver chloride is a slightly soluble salt. So if we take solid silver chloride and put it into water, it's going to start to dissolve. And since it's an electrolyte, it's going to break up into the ions in solution. But as those ions are formed, eventually the reverse reaction is going to start until we get to an equilibrium where the rate of dissolving in the forward direction equals the rate of precipitating in the reverse direction. At that point, we have a saturated solution. So a saturated solution is a solution that's at equilibrium between the dissolving of the solid and the precipitating of the ions. Now, since it's in equilibrium, we can write a K expression. Okay, so over here, we just have a little picture. These little red and white things, there's water. Here's our silver chloride. A little bit of the silver ions and chloride ions are going to come in the solution, and eventually we're going to have a saturated solution. The K that we're going to look at now is called our solubility product constant. So we looked at Kc values, which was just a generic equilibrium constant in terms of concentrations. We had Kp, which was in terms of partial pressures. We looked at Ka values when the substance was specifically an acid, or Kb when it was specifically a base, or Kw when we were looking at water. When we look at slightly soluble salts, we're going to use Sp, which stands for solubility product. So Ksp is the solubility product constant. Now, we write it the same way we write any equilibrium expression. It's the products over the reactants raised to the power of the coefficient in the balanced equation. But remember again that we don't include solids and liquids. So the concentration of silver ions times the concentration of chloride ions would be our Ksp expression. Now, just like we can look up Ka values on a table and we can look up Kb values on a table, we can look up Ksp values on the table. And silver chloride has a Ksp of 1.6 times 10 to the minus 10. So what can we do with that? Okay, we're going to be able to calculate concentrations from Ksps. And because this value is really small, it tells us that Ksp is very insoluble. There isn't much of it that's going to dissolve at all before we establish equilibrium. All right, so how do we write Ksp expressions? Let's say that we have this generic solid here, AB. Okay, and then we've got the subscripts, which give us our formula. When it dissolves, it's going to dissolve into A ions and B ions. And the ratio is going to be B to A. So when we go to write our Ksp expression, it's going to be the concentration of A ions raised to the A power times the concentration of B ions raised to the B power. And looking at this, this A and B are backwards. This should say A to the A, B to the B. So this A and B are switched, actually. Sorry about that. That's a typo. So we're looking at our solubility product constants. Notice that we don't include this solid in our Ksp expression. All right, so let's get some practice. Okay, let's write the equilibrium reaction and the Ksp expression for these three examples, and we'll do the first one together. So for the first one, we have copper bromide. Now, copper has a -1 charge. We get that off the periodic table. So bromide has a -1 charge. So the copper has a +1 charge. So when we go to write our equilibrium reaction, the copper bromide is going to break up into copper ions and bromide ions. So from there, if we want to write our Ksp, it's the concentration of copper ions times the concentration of bromide ions. All right, so see if you can write the equilibrium reaction for mercury 2 iodide and then write the Ksp expression. Don't do the last one yet. Let's do one at a time. We'll do them together. So the mercury 2 iodide is going to make up into mercury ions and iodide ions. Now the charge on the mercury comes from this 2, and the charge from the iodide comes from the 1, which is assumed. So that's where this +2 and this -1 comes from. And then to balance it, since we've got 1 mercury here, we want 1 mercury here. And since we have 2 iodides here, we want 2 iodides here. So there's our equilibrium reaction. So to write the KSP, the concentration of mercury ions times the concentration of iodide ions squared. All right, now the last one. This is silver sulfate. SO4 is a polyatomic ion. Don't break this up. Okay, silver sulfate. Write the equilibrium reaction and then write the KSP expression. All right, so we're going to produce silver ions and we're going to produce sulfate ions. There's a 1 assumed to be out here, so the charge on the silver is a +1 and the charge on the sulfate is a -2. So that's where this +1 and -2 comes from. We have 2 silvers on the reactant side. So we need 2 silvers on the product side. And we have 1 sulfate on the reactant side. So we need 1 sulfate on the product side. So the KSP would be silver ions squared times sulfate ions to the first, and we wouldn't write that, we just assume it. So the very first step, just like when we were looking at our acid equilibrium or a base equilibrium, we need to write out the equilibrium reaction. And then from the equilibrium reaction, we can write the KSP. And then the questions kind of work in one of 2 ways. Either we're given the concentrations and we want to calculate KSP, or we're given the KSP and we want to calculate the concentrations. So the molar solubility is defined as the moles of solute per volume of solution, or the molarity. And the solubility is the equilibrium position, how much of it actually dissolves. If we know the solubility, we can calculate the KSP. And if we know the KSP, we can calculate the solubilities. Now, it works really well for compounds where the cation has a +1 charge and the anion has a -1 charge. It's more of an estimate when they're not +1 and -1, but we would only calculate estimates anyway. All right, so here's a question. A student measures the molar solubility, how much dissolves, of barium phosphate. We're given the formula. Okay, barium is a +2, phosphate is a -3. We're told that the concentration, the molar solubility, is 6.46 times 10 to the -7. That's a really small number. It's not very soluble. We want to calculate the KSP, the solubility product constant. So let's do it step by step. First thing, write out the dissociation of the salt. Write out your equilibrium. Keep in mind what the charge on the barium will be, what the charge on the phosphate will be, and how many barium ions and how many phosphate ions will you have in that equilibrium. All right. So barium phosphate is going to break up into barium ions and phosphate ions. Now, the charge on barium is a +2. That's where this 2 came from, if we remember how to write formulas. The charge on phosphate is a -3. Again, that's where that 3 comes from. Now we've got 3 bariums, so we need 3 bariums on the product side. We have 2 phosphates, so we need 2 phosphates on the product side. And we've got our arrow going in 2 directions. Now, we can write a KSP expression from this. So write what your KSP expression would be. Okay, remember, we're not going to be including solids, so the barium phosphate will not be in your KSP expression, just the barium ions and the phosphate ions. Now, well, I kind of went ahead of myself. So the barium ion will be 3x, and the phosphate will be 2x, and x is how much dissolves. Sorry, I should have done that part first. Actually, I should have done it second. Here's our KSP expression. Okay, so KSP equals the barium ion concentration raised to the 3 times the phosphate ion concentration raised to the 2. Now, for the barium ion concentration, that value is going to be 3x because of this 3. And the phosphate ion concentration is going to be 2x because of this 2. So we're going to substitute those in. So we get 3x cubed times 2x squared. Now, let's talk math-wise a little bit. If we've got the quantity 3x and we're going to cube it, that means we're going to cube the 3 and we're going to cube the x. So 3 times 3 is 9. 9 times 3 is 27. So 3x cubed equals 27x cubed. Now, 2x squared, we're going to square the 2 and we're going to square the x. So we get 4x squared. So 27x cubed times 4x squared gives us 108 x to the 5th. Now, the question gave us x. It gave us the molar solubility of barium phosphate, and it's a 1 to 3 ratio to get to barium ion and a 1 to 2 ratio to get to phosphate. So we're going to take that 6.46 times 10 to the minus 7 and substitute it in for x. So 108 times 6.46 e negative 7 raised to the 5th power. Do the exponent part first. Remember your PEMDAS rules, order of operation. Exponents come first, then multiplying comes second. So practice that in your calculator before I give you the answer. 6.46 e negative 7 raised to the 5th power equals times 108. Okay, and while you're putting that in calculator, there was a question about where the 108 came from. So we're going to take 3 and cube it. That gives us 27. We're going to take the 2 and square it. That's going to give us 4. 27 times 4 gives us 108. And then we've got x cubed times x squared. We add exponents, and that's where that x to the 5th comes from. Does that clear that up, Jacob? You okay?
Yes, thank you.
You're welcome. All right, yeah. 1.22 times 10 to the minus 29. Think about what this number means. Okay, it's the concentration of, actually it's not, it's just giving you, sorry, it's just giving you a value that's the product of the ions in the solution. And look at how small it is. Negative 29. Remember we said when Ka values were small, we were looking at weak acids, and when Kb values were small, we were looking at weak bases. Well, KSP values are going to be small because only a very small amount of this solid actually breaks up into ions in solution. All right, so let's try another one. Okay, a student measures the carbonate ion concentration in a saturated aqueous solution of silver carbonate to be 1.24 times 10 to the minus 4 molarity. Calculate the solubility product constant, KSP, for silver carbonate. Well, the first thing we have to do is write the formula for silver carbonate. And I'll give you a hint that silver is Ag with a +1 charge. Hopefully we remember that, but maybe we don't. So silver is an Ag with a +1. Here's carbonate. CO3 with a -2. So we want to write the formula for silver carbonate and then write the equilibrium reaction for that solid dissolving in water. Don't go any further. Let's just do it kind of step at a time. So write the formula for silver carbonate and then break it up into its ions. All right, so silver's a +1, carbonate's a -2. So silver carbonate's Ag2SO3. It's going to break up into silver ions that have a +1 charge and carbonate ions that have a -2 charge. We have 2 silvers on the reactant side. We need 2 silvers on the product side. We have 1 carbonate on the reactant side. We need 1 carbonate on the product side. All right, so there's our equilibrium reaction. From that, write your KSP expression. Remember, it's the concentrations raised to the power of the coefficient in the balanced equation. Oops, I keep forgetting that this part comes up first. This is 2x. This is x. And this time it gives us the carbonate ion, so it's giving us what x equals. It's going to want us to figure out what the silver carbonate is. I need to change the order of this. Oh, all right. So there's our KSP. Okay, the silver ion concentration squared times the carbonate ion concentration to the first. And again, it's a 2-to-1 ratio. So silver ion is 2x, whereas carbonate ion is x. This question gives us the carbonate ion. So this question's giving us x. So we're going to substitute in 2x for silver. And we're going to substitute in x for carbonate. So we get 2x squared times x to the first. Now, 2x squared, we're squaring the 2 and we're squaring the x. So this becomes 4x squared. 4x squared times x gives us 4x cubed. Now, the question gave us x. We're going to substitute that in here. we can calculate what the KSP is. Order of operation, exponents come before multiplying. So 1.24 e negative 4 raised to the third power equals times 4. Plug it in the calculator and make sure you know the order of operation for these kinds of calculations. Square comes before multiply. (1.24 e negative 4 cubed equals multiplied by 4. Okay, if we put it in right, 7.63 times 10 to the minus 12. Again, 10 to the minus 12 is a really small number. That tells us that only a very small amount of that silver carbonate actually breaks up into ions in solution. All right, so let's look at this one. It gives us the KSP is 5.0 times 10 to the minus 5. We want to calculate the molar solubility of silver bromide. All right, so let's write the equilibrium equation first, equilibrium reaction. The charge on silver is a +1 and the charge on bromide is a -1. Okay, so here's our silver bromide. It's breaking up into silver ions and bromide ions. And it's a 1-to-1 ratio. So X and X, 1-to-1. Also means this is X amount dissolved. So now we want to write a KSP expression. So write your KSP expression. Okay, so the concentration of silver ions times the concentration of bromide ions equals KSP. Now, this time, we know KSP. You can plug that in here. We don't know the concentrations. But we do know that the concentrations are equal to each other. So we're going to be able to plug in X for silver ion and X for bromide ion. That really equals X squared. And if we want to solve for X, we would just take the square root of both sides. So again, do that in your calculator. Make sure you know how to take the square root of numbers that are written in scientific notation. There's a couple of different ways you can do it on your calculator. So take the square root of 5.0 times 10 to the minus 5, and then we'll compare your answer. Okay, I get 7.1 times 10 to the minus 3. That's the molarity or the concentration or the moles per liter for silver ions in the solution. It's also the concentration of the bromide ion in the solution, which is equal to how much of the silver bromide actually dissolved. And that's what molar solubility means, how much of it dissolved. All right, so let's look at another one. What's the molar solubility of silver sulfite if the KSP is 1.5 times 10 to the minus 15? Now, silver is Ag plus 1. If we don't remember sulfite, sulfite is SO3 minus 2. So here's our equilibrium reaction. Okay, silver's a plus 1. Sulfite's a minus 2. So we're going to produce silver ions and sulfate ions. There's 2 silver ions here, so we need 2 here. There's 1 sulfite here, so we need 1 here. So once we have that, it's the same kind of problem as we had before. Now the ratio of silver to sulfite is 2 to 1. Oops, of course I didn't do it that way this time. So keep that in mind. Write your KSP expression. Think about what silver ion will be, since we have this 2 here. What sulfite ion would be, since we have a 1 assumed to be here. You know the KSP. See if you can calculate the molar solubility of silver sulfite. So we've got silver squared times sulfite to the first. 2x for silver, x for sulfite. Okay, do your math, solve for x. X is your molar solubility of silver sulfite. The quantity 2x squared equals 4x squared times x equals 4x cubed. Now, this time you're going to be dividing by 4. That'll give you x cubed. And then take the cubed root of both sides. And that'll give you x. Okay, divide both sides by 4. Then take the cubed root of both sides, and that'll give you x. And the cubed root is the same thing as raising it to the 1/3 power. Okay, so 1.5 e negative 15 divided by 4 equals, and then use that little caret on your calculator. Raise it to the 1/3 power. Try that in the calculator. Make sure you're getting 7.2 times 10 to the minus 6, and then we'll talk about what that number means. Anybody have any questions on where that came from? Are you getting that on your calculator? Now, what does that mean? Well, that's x. So that's how much sulfite ion would be in the solution. If we were to multiply x by 2, that would be the amount of silver ion in the solution. And X is the amount of silver sulfite that dissolved. And the amount of silver sulfite that dissolves is what the molar solubility is, and that's what we were asked for in the question. All right, let's just do this last one for today. Just adds a different step onto it. So it says calculate the mass. Calculate the mass of silver iodide that can be dissolved in 2.50 liters of solution, and it gives us the KSP. All right, we're always going to be doing the same steps. So let's write the equilibrium reaction first. Silver is Ag with a +1. Iodide is I with a -1. So that means silver iodide is AgI. Break it up into its ions. Okay, so Ag is a +1, I is a -1. There's silver iodide. It's going to break up into silver ions and iodide ions. And it's a 1-to-1 ratio. So X for silver ions and X for iodide ions. All right. So now write your KSP expression. Plug in X for silver ion and X for iodide ion. And 1.5 times 10 to the -16 for KSP. And calculate the molar solubility. Don't go any further than that yet. Okay, just do the molar solubility like we did on the previous slides. Okay, so write your KSP expression. Plug in X for silver ion and iodide ion. Solve for X. Okay, so KSP equals the concentration of silver ions times the concentration of iodide ions, which equals 1.5 times 10 to the -16, which equals X squared. Solve for X, you need to take the square root of both sides. So 1.22 times 10 to the -8 is the concentration of silver ions in the saturated solution. It's the concentration of iodide ions in the saturated solution. And it's also the amount of silver iodide that dissolved. All right, so now we're going to kind of go back to our solutions chapter. We know the molarity. And we know the volume of the solution. We can calculate the moles. And if we know the moles and we know the formula, we can calculate the mass. So we take the molarity and multiply it by the volume. This gives us moles of silver iodide. Multiply it by the formula weight for silver iodide. This came off the periodic table. And now we know how much silver iodide actually dissolved in that 2.50 liter solution. Look at how small that is. 7.16 times 10 to the -6 grams. Because silver iodide is only very marginally soluble, has a very small KSP value. And actually, at least I think, once we've done, acid-base equilibrium and the things we've been working on, I think KSP might be just a little bit easier, at least the beginning parts. Hopefully you feel that way. It's also that we've been doing equilibrium for a while, so that should hopefully make it a little bit easier as well. So I think we're going to wrap up for today. I'm going to stop recording.